Hi students, so today we begin lecture 58 on our aerospace engineering course, and today I'm going to start the space mechanics part of this syllabus. So today we are going to discuss the orbit equation. So essentially we are going to motivate why we need to study space in this course and then look at this particular equation, which is the bedrock of the motion of many of the space vehicles. I'm Dr. Ranjan Ganguly. So let us take a look at the most important space vehicles. So here I have made a picture of the Earth, and from this picture you can see some planets. For example, here we have Mars, we have Moon. So you have heard of the Moon mission and the Mars mission. In these situations, essentially we have rocket type of vehicles which fly to these planets or satellites respectively. Now, while the Moon is a typical satellite of the Earth, there are also many satellites which are circling around the Earth at any given time, and these are satellites which are used for a variety of purpose. For example, they are used for communication, so you can get a lot of your TV, your cable TV, and so on from the satellites. They also form the bedrock of the system such as the GPS, that is the global positioning system. So if you are somebody who uses Google Maps or Apple Maps or anything like that, you know that you can go from point A to point B on the Earth, and in this kind of situation, you are often using the GPS satellites here. So the satellites are actually the bedrock of the navigation systems today. So whether you are in a car, whether you are in a ship, or you are flying in an airplane, the pilot is probably using some kind of navigation system based on satellites. Now, beside that, there are some vehicles like the space shuttle type of vehicles I've shown here, which essentially take off from Earth. They do their mission in space and they come back. So these are essentially known as re-entry vehicles. Then there are of course vehicles which simply go on a one-way mission. For example, if you have a mission to Moon or Mars, very often the vehicle goes there and does not return. There is a robotic probe which essentially does the investigation on that planet or satellite. So essentially now you see that we will have to do certain things which we have not done before. The first thing is that if you are a satellite, you have to rotate around the Earth or revolve around the Earth in some orbit, and you need to have a certain velocity to do that. So there is a velocity known as circular velocity, that is about 7.9 kilometer per second. We are going to see how we can derive this circular velocity. There are also situations where you simply need to leave the Earth's atmosphere. These are the case of lunar and interplanetary vehicles. Here you need something known as the escape velocity. So your vehicle must have a velocity greater than 11.2 kilometer per second in these cases to leave the Earth's atmosphere. So now we are going to look at the atmosphere and also vehicles which leave the Earth's atmosphere. So these things are going to become important. So if you are somebody who is ever going to take part in anything to do with space, satellites, and so on, these lectures are going to be very important for you. So let us look at a typical situation. So here let us say there are 2 points on Earth. There is a city here, there is a city here, or maybe there is a particular takeoff strip here and a take landing strip here. And what happens is that the rocket takes off here. So this is the ascent phase, and then it does its mission. Maybe it deploys a satellite and then it crashes off here. Sometime it crashes into the sea. That is typically the most liked case, and so that is something which will happen. If it's a re-entry vehicle, it will go and it will land here somewhere. Sometimes these locations may be the same if you have a re-entry vehicle, or they may be different locations also. Now here I have shown in red what are the limits as far as the atmosphere is concerned. So the atmosphere is the region where you have air with regular density where aircraft are typically flying. So you know this typical aircraft such as a Boeing 777 or a Airbus A350 would be flying somewhere here at a height of about 10 kilometers or so. So you may have to fly much beyond this height to essentially keep a satellite in space. So these are the launch vehicles which do that. So now we are going to make use of certain laws of physics which are actually pretty classical. So we will start with Newton's law of gravitation. So this law essentially says that the force between two masses given by small m and capital M is equal to gmm by r square, and here capital G, big G, is known as the universal gravitational constant. So that's a very important constant as far as physics is concerned, and its value is 6.67 into 10 to the power minus 11 meter cube per kg second square. So we can consider a situation, for example, if we have the earth and maybe we have a planet here, maybe this is the moon, then what would happen is that there would be a force between these two bodies here. So here we may say that earth is represented by this mass m, capital M, and the planet or satellite is represented by this mass small m. The distance between the centers is given by the small r here. Then we can actually calculate this force. Now you can of course clearly see that this goes with the intuitive reasoning that if this distance becomes extremely large, the force becomes very small. So the force is inversely proportional to the r square, and also the fact that if these masses are very large, then that's going to also have an impact. So suddenly you can see that in the regular world, if there are two small masses, then this force is going to be very small. So maybe you can do a calculation where you can take yourself and your friend, separate yourself by some distance, and then calculate this particular force here. You are going to find that it is pretty small because this number is there, 10 to the power of minus 11, which is going to dominate your force. But do remember, planets and so on are pretty large. So for example, there is a force typically acting between any planet and its moon. So now we are going to turn to some more things in physics, because we are going to try to write the equation governing the motion of this mass small m. So let's first calculate the potential energy of this system. So we will denote it by the letter phi. So here we know the force is given by g mm by r square from Newton's law of gravitation. So we can say that d phi is F into dr. So that is basically from the formula for work. So the force into a small length dr would give us the potential energy corresponding to that force and that small length. And so that gives me gmm by r square into dr. So this is the incremental component of the potential energy of the system because of this small length dr. So now I rewrite that fact here, that d phi equals fdr, which is this expression here. And now I can do this integration. So essentially what I do is I integrate the d phi term from 0 to phi, and I integrate the gmm by r squared term from infinity to r, where we use a convention which is very typical in astronautics, that phi is 0 when r is infinite. So if you look at the bottom part of this definite integral, the 0 goes with infinite here. So that's something we have to keep. And then r goes with the value phi. So this is by convention. We have to make some kind of baseline somewhere so we can compare the potential energy of the system. So now we know this formula, so we can quickly integrate it. It's a very simple integration. So once we do this integration, we get this equation here. So once we get this equation here, we can very clearly see that when you put r is infinite, you get this equation here. So it's something which is very clear here, that you can do this integration problem without any issue, and you can get the expression for phi. Now phi is negative gmm by r. So now let's turn to the kinetic energy part of this formulation. So we again start with the earth with the mass m, the planet with the mass small m, and now we say that this planet, satellite or moon has a velocity small v. So the kinetic energy of this system is going to be half m into v square. So I can now write this kinetic energy in terms of polar coordinates, which is going to help us in our calculation. So let's compare these two bodies, and we can clearly see that we can express this satellite here using the distance r, which is this distance, and the angle theta between the horizontal and this line here. So now we can clearly see that this mass small m, it's going to have a certain velocity here given by r dot, and there is also going to be a component here given by r theta dot. So these are all coming from circular motion concept. So there is like a motion in this direction. So there is going to be a theta dot, and so this velocity is r into theta dot here. So the velocity v can be split into these two components, r dot and r theta dot. Therefore, I can write t is half mv square equals half m, and then v square is basically r dot square plus r theta dot square. So this will give us the velocity of this particular system. So the fact that v is equal to this value here, you need to keep in mind. So we can express it in this form using the theory of forces and the parallelogram of forces. So now that I have t, I have phi, I am able to immediately write the Lagrangian. So we are going to use Lagrange equation to derive the orbit equation. So the Lagrangian is defined as B equals T minus phi, which is the kinetic energy minus the potential energy. And so immediately I can write the equation for T, which I have given in this light blue box. And also I can write the equation for phi. And so the negative sign becomes positive, and I get this gmm by r term here. So this is a very important equation. It tells us the Lagrangian B, and it essentially includes the energy concepts about the system in one simple expression given by B. Now we are going to typically make a different nomenclature in most cases about gm or G capital M. So let's look at that. So let's rewrite B here. We already know G is given by this value 6.67 into 10 to the power minus 11 meter cube per kg second square. Now the mass of Earth is 5.98 into 10 to the power 24 kg. So since we are Earthlings, we are going to see that Earth is our point of reference. We are going to put this capital M as Earth mass, and now what we are going to do is we are going to multiply G into M, and so we get this value here which we call k square. K square is 3.986 into 10 to the power 14 meter cube per second square. And this value k square is known as the geocentric gravitational constant, because you clearly see that we have now centered our concept to the earth. So we have assumed that capital M belongs to earth, and so we have obtained this value. Now the formula gmm by r is very generic. So if you are dealing with Saturn and its moon, you can use that formula, but then you have to use the mass of Saturn as capital M here. Once we become geocentric, that we become fixated on earth, we can use k square is G capital M. So let's again now write the Lagrangian, and we are going to immediately realize two things. We are going to realize that this is a function of r and theta, so we are dealing with polar coordinate situation. And also I have replaced the capital Gm by k squared, so I have got this equation here. So this equation is nice in a way because we of course know that capital G into M is positive, so we can write k square because we then know that this is always a positive term. So with this B, now we are going to try to get the Lagrange equations. So the Lagrange equation is given by this formulation here. So remember there are two coordinates, that is theta and r. So first we are going to take the equation with respect to theta, and then I'm going to take it with respect to r. So if you're not familiar with the Lagrange equation, you can go back to physics or mechanics or vibrations books, and you will find that equation there, and they will give you some problems such as the pendulum or the spring mass system with which they will illustrate the Lagrange equation. So let us take our B here, which is the Lagrangian, and then we are going to apply this Lagrange equation based on theta to this equation here. Now you fortunately see that there is no theta in this equation, there is only theta dot, so this part is simply not there, this is 0. So we get d by dt into delta b by delta theta dot. So if you differentiate b by theta dot, you clearly see you get the term half m, and you get here the term r square and 2 theta dot. So the 2 and 2 cancel out, so you are left with m r square theta dot. So this equation is here, and this equation essentially simply tells you that m r square theta dot is a constant, because if this is a constant, if I were to differentiate it with respect to time, essentially this would become 0 because derivative of a constant is 0. So this equation mr square theta dot is constant gives me the first physical equation which we get for this mass m here. I have replaced this mass m by a satellite because most of the time we will be thinking about satellites, because satellites are far more numerous than, for example, the moon, which is only one as far as Earth is concerned. So we can write this as a fact of physics that angular momentum of the spacecraft is constant, because if you have a point mass, I is mr square, and therefore this equation is the same as I theta dot equals constant. So essentially this is telling us that this particular value, as far as it is concerned, it is constant, and so angular momentum of the spacecraft is constant. Now we look at the second equation, which is the orbit equation, or we are going to get the orbit equation out of it, and that is by using the Lagrange equation with respect to r. So remember, we had one coordinate theta and the second coordinate is r. And so if you do that, you start with b, you apply the second Lagrange equation here, and now you have to differentiate with respect to r dot and r. So if you differentiate with respect to r dot, you simply get the term m r dot here. So that's the term which comes here. And if you differentiate with respect to r, you're going to get two terms. One of the term involves the k squared term. So that's going to become negative mk squared by r square. And as far as this term is concerned, it is going to become mr theta dot square, because remember r got differentiated. So the r square became 2r, 2 got cancelled, and so you ended up with the mr theta dot square term. So essentially this is the equation which comes out of the second Lagrange equation with respect to r, that is mr double dot minus mr theta dot square plus mk square by r square equal to 0. So now let us summarize some of the things we have got till now. We saw that mr square theta dot was constant, and so theta dot is a constant if m is constant. We also saw that h is r square theta dot is the angular momentum per unit mass, because remember, if I were to take mr square theta dot divided by m, I would get r square theta. So that's basically nothing but the angular momentum I theta dot divided by m, so that is per unit mass. So let's just think of h as r square theta, and we are going to use this in the equation. So we again start with the orbit equation here. I have shown that in the light blue, and then what I do is that I multiply the second term here by r cube both on the numerator and the denominator, and so I'm going to get a r4 on top and r cube below, and so I can immediately then write this theta dot square r4 term as h square. So I get the orbit equation in this form, where essentially I have divided by m throughout and got rid of m, assuming of course that m is not equal to 0, which is the case because you have a real satellite out there. So now this is the equation, the orbit equation. R is of course a function of t, theta is a function of t. So this is a differential equation with respect to time. The dot of course represents the derivative with respect to time. So let us write out what we have discovered today. We see that there is a mass here, typically the Earth, there is a satellite, there is a distance r, there is this angle theta, and of course we also have found out what is k square value, and we know that h is the angular momentum per unit mass. Now using some of these things, k square and h, I can write the orbit equation here. So all the remaining things like r double dot r are essentially related to this r here, the distance between the Earth and the satellite. H is the angular momentum per unit mass. K square is the GM value, or the geocentric gravitational constant. So that will be a simple constant here. So now we can see that this important equation, the orbit equation, will apply to many vehicles or spacecraft in orbit. They of course will apply to a satellite. They may also apply to, for example, rockets and different aircrafts given different conditions. So two critical equations we have derived today. The first is that angular momentum of the spacecraft is a constant, and the second is the orbit equation. So this equation is somewhat more difficult to solve. So we are going to try to solve it in our next lecture. And remember, again, it's a differential equation with time, and so therefore it's going to require initial conditions to solve. And also it is a very simple ordinary differential equation. So we are going to take recourse to the theory of differential equations, which you must have studied in engineering mathematics. If you're not familiar with that, just browse up through some engineering math books such as Jig and so on. And then we will solve the equation in the next class and proceed further. So I'll end this lecture now, and I will see you in a video sometime soon. If you have any comments about this lecture, please leave them in the comment section below, and make it a point to subscribe to my channel, because that's something YouTube algorithm likes, and if YouTube algorithm likes something, then we need to respect that.